When I first heard that there is a possible connect between the area of a rectangle and a quadratic expression, I was like, what? I was blown away. A lot of the information that I'm going to share in this particular video and in the video that will follow is borrowed from ideas that I learned from Dr. James Tanton. A huge shout out to Dr. James Tanton. I'm going to share some of his videos in the description box below. Please go and take a look at some of his lectures. It's wow. For starters, if we think of multiplication of two numbers, something like, let's just say 27 times 38, all right? What do we do? Traditionally in our schools, we are taught to multiply something like this. Okay, we write 27 and then we write down 38. Can you guys see this? All right. We write them down as a column and then we multiply, right? We go ahead and multiply 8 and 7 is 56, 8 to 16 and 5 is a 21. Then we put a 0 here. We're taught, okay, put a 0 here. And then we say 3 and 7 is 21 and 3 and 2 is a 6 and that 2 is an 8 and that should be 6, 2 and 10. Okay, so what did we do here? We have actually added something here, right? We've added something here. That's important to understand. What happens is sometimes when you do all this multiplication, it's not wrong. Okay, this technique is correct. And that's all that's taught in school. There should be some place I feel that students are allowed to think what's going on. What's going on? Even in my videos, I've emphasized that, you must learn your multiplication tables to be able to write down the factors of a quadratic expression within 10 seconds, under a minute. The more multiplication tables you memorize, that's good for you. And that's good, right? It's good. But like I said, there's a time and place for something like that. At the same time, there should be a time and place where we can just pause and try to see what's going on. Our exams don't encourage this kind of reasoning because in our exams, we just asked to multiply and give the answer and go to the next question. And when we get caught up in the process of algebra, whether it's factoring or whether it's multiplication, we sometimes are not able to really see the beauty, the basic principles that lie underneath all our mundane, boring, everyday mathematics. Okay, that being said, let's go on with it. Okay, so there's two numbers that we multiply and there's a 0 that we add, and then we add these things, right? And then we get the answer. And the same method we use for 3 digits, maybe even for decimals, everything works, right? Now, I want to offer another method. Now, this is not my original method. I saw this method in a textbook. It's called the grid method. Let me write down the name, okay? You might have come across this method under a different name, okay? Grid method. Can you see that word? Okay, that's grid method, and it's skipping away. Grid method, okay? That's called the grid method, GRIDMETHOD, grid method. What this method does is something like this, okay? 27 times 38, you write it like a grid, almost like a rectangular grid, that is. And what are we doing is that we're basically chopping up the numbers 27 and 38, chopping them down to simpler numbers. So 27 can be written as 20 and 7, correct? And in the same way, 38 can be written as chopped down as 30 plus 8. So what have we done? 27 and 38 has been chopped down to simpler numbers, 20 and 7, 30 and 8. And now you might be thinking, well, this is like elementary school mathematics. Yes, it is like elementary school mathematics. And initially, this method might seem too cumbersome and you say, hey, this is much more easier. It may be easier because you're used to it. But somehow this method may be easy and gives us all the right answer. But like I said, it doesn't make us pause and see the underlying principle, which is why I offer the second method. If you've seen it, great. If you've never seen this before, just give me a few more seconds and you'll understand why I find that this is so fascinating. And it might take a little more longer if you're doing it for the first time, but bear with me. All right, let's multiply each cell at a time. All right, so perceive this as a smaller rectangle. Okay, the length of the rectangle is 20. Well, actually the length should be longer, but it'll give you the idea, the geometry, the shape. I've not drawn it to scale, but the idea, focus on the idea, not the perfectness of this geometrical figure that I've drawn, okay? So here we go. 2 times 3 or 20 times 30 should be 600. Easy to multiply that? All right. In the same way, 30 times 7. This is the second rectangle out here. All right. Again, the geometry is not perfect, but the idea is going to be right. Okay, that should give us 210. And then this third rectangle out here, all right, that's 8 and that's 20. This is 8 and this is 20. So 8 times 20 is like saying that's 160. And then 8 times 7 should give 56. All right, so basically what we've done is that we've chopped down those numbers, 27 as 20 and 7 and 38 as 30 and 8. And we've got these 4 smaller rectangles. I'm just going to, that's one rectangle, that's another rectangle, that's another rectangle, and that's, not only is this making the multiplication easier, it's making me see something more. It's making me see that, okay, the area of this rectangle is 600, right? Area, the formula for the area of a rectangle is length times width. So 30 times 20 can be perceived as the area of a smaller rectangle. And the same way, 30 times 7 is the area of this other rectangle, the second rectangle, whose area is 210, which is the same thing as multiplying 30 and 7. Likewise, the area of this third rectangle is 160. That's just the multiplication of 8 times 20. Simpler numbers, all right? In the same way, 8 times 7 is 56. That's the area of another rectangle. So when you want to find the area of the entire rectangle, which in other words, it is 27 times 38, right? That can be perceived as a rectangle whose one side length is 38 and the other side length is 27. I've deliberately called it one side length and the other side length and not length and width because, you know what, my geometry is not accurate, right? I've not, but the idea is accurate. I hope you can appreciate the idea, right? So in one sense, the area of this rectangle, the multiplication of the two numbers, is just, you can just add up all these individual areas, right? It's just like saying that it should be 600 and 210 and 160 and 56. So when you add it up, you should get 600 and 210 is 810, 810 and 160 is 910, 970, 970 plus 56, 970, let's do that, 56 should give 6, 2, and 10, 1026, 1026 by both the methods. The conventional method, let's call this the conventional method, and this is the rectangular method or the grid method. You get the same answer when you add. So what's different? Yes, this might seem a little long to you initially and might say, oh, well, that is much more easier. But look at the principle. We're still adding, right? We're still adding the two pieces here. That's very much similar to adding those different rectangles. And what more? Why do we add that 0 here? That's like saying that's the place value for 30. The place value is not just multiplying by 3. Actually, it's the place value 30. So in one sense, we are still following the place value technique in the grid method. 20 and 7. It's like saying 27. 2 comes in the tens place. 7 comes in the units place. So this is 20 and that's 7. 38 in the same way is written as 30 and 8, which means 30 is in the tens place. And so the place value is still maintained, and that's why this works. Now we can extend this idea, this grid method, to even larger numbers, 3-digit numbers also. So if you have some number like, 432 times, let's say 27 again, all right? So it's a 3-digit number and a 2-digit number. Let's try the grid method, okay? So I'm just going to make a grid, a rectangle, and let me try and see whether I can chop it off in somewhat realistic measures, okay? Earlier my rectangles were not right. So this is going to be 400, this is going to be 30, and this is going to be 2. I hope you understand the technique. So it's 432, 432, all right? In the same way, the place values are upheld. 27 can be chopped down to 20 and 7. Now, these are simpler numbers to multiply, all right? So 400 times 20 should be 8,000, okay? And 20 times 30 should be 600, and 20 times 2 should be 40, and this should be 2800, and this should be 210, and this should be a 14. Now that means that if this method is a legitimate, valid method, then the multiplication of 432 times 27 should just be the sum of all these individual numbers, 8,000 plus 600 plus 40 plus 2,800 plus 210 plus 14, right? It's as good as saying the area of this entire rectangular piece whose length happens to be 432 and whose width happens to be 27 is the same as the sum of the individual areas, these small chopped up rectangles, right? So it's just like saying it's 8,000 plus 2,800 plus 600 plus 210 plus 40 plus a 14. So when we add this thing up together, it should be 8,000 and 2,000 is 10,000. 10,000 with that 800 and 600 should be 11,400. 11,400 with the 200 should be 11,600. And 10 with that 40 is 11,650. 11,064 should be the answer. Okay, so that's 11,664. All right. So the total happens to be 11,664. You can check that out on your calculator. I love this method, the grid method. You can try it out even for fractions for a couple of reasons. Okay. First reason I like that it gives me a meaning to the multiplication of two random numbers. And just multiplying any two numbers, a times b, it gives me a meaning to that. It gives me the meaning is that it's actually finding the area of a rectangle whose length happens to be a and whose width happens to be b. The area of a rectangle whose length happens to be a and whose width happens to be a times b. And this is just a geometrical perspective, okay? Which also means that if it's the area of a rectangle, then if I keep this rectangle in its horizontal position, let's say that this is the horizontal position and the same rectangle, okay, without changing its dimensions, if I just turn it around and keep it in its vertical position, that's the vertical position. That means this is now my b, and that's my a. Okay, I've just turned it around. Would the area change? The area of the rectangle won't change because we've just changed its orientation from a horizontal position to a vertical position. So if a times b represents the horizontal side times the vertical side, then in this orientation, b times a would represent the horizontal side times the vertical side. And because the area has not changed, we can say that a times b is equal to b times a. And that is the multiplication law of commutativity. Commutative, we say multiplication is commutative, means a times b is equal to b times a. In other words, as I explained using the rectangles, that if a is the horizontal side, or the first number being the horizontal side and the second number being the vertical side, and when we change the orientation of the rectangle, the horizontal side and the vertical side get switched, which means a times b will become equal to b times a. We call it the commutative property of multiplication. So all these properties really come to life when you actually see multiplication as the area of a rectangle. Now, the second thing that I really like about this method is that if multiplication of two numbers, any two numbers, can be interpreted as the area of that rectangle whose dimensions are those two numbers, then you should be able to generalize this for any numbers. And by any numbers, I mean, you can take even something with x, right? X represents any number. So what if this length was something like 3x and this part is 2? So it's 3x plus 2. The length of the larger rectangle, the length of this larger rectangle is 3x plus 2. This much is 3x. X is any number. So 3x is any number, multiple 3 times that any number. And this part is just 2. And let's just say that the width of this rectangle here is 2x plus 1. All right. The width of this larger rectangle is 2x plus 1. So we've got this piece is 3x whose width is 2x. This piece, the width is 2 and the length is 2x. This piece, the length is 3x and the width is 1. And for this piece, the length is 2 and the width is 1. As such, when we multiply, again, let's use the grid method because we're trying to generalize for any number x. This area of this rectangle, 3x times a 2x would give me 6x squared. 2 times 2 would give me 4x. 2 times 2x gives me 4x. That's the area of this rectangle. Then 3x times 1 gives me 3x. That's the area of this rectangular piece out here. 2 times 1 gives me 2. That's the area of this rectangle. That means now when I add up all these individual areas, that will give me 6x squared plus a 4x plus a 3x plus a 2. This should be the area of the larger rectangle, that entire piece, which is what? Which is 3x plus 2, the length times, can you guys see what I'm writing? I hope so. Let me share that. Okay, there we go. 3x plus 2 times 2x plus a 1. Can you see the whole thing? Let me see if I can zoom out. There you go. Now you can see better. Right? Now you can see better. So the length of the larger rectangle was 3x plus 2. The width was 2x plus 1. And the individual areas when we add it up gives us 3x plus 2 times the 2x plus 1. This is just multiplying those two numbers, generalizing the multiplication of two numbers. But on the left-hand side, what do we have? On the left-hand side, when we simplify, we have 6x squared plus a 7x plus a 2 equal to the area of a rectangle. Length times width, the area. This we already have identified as the area of the rectangle. But on the left-hand side, what do we have? we have a quadratic trinomial. Now, isn't that bizarre? The quadratic polynomial can be perceived, can be seen as the area of a rectangle, a four-sided figure whose length is 3x plus 2, whose width is 2x plus 1. We had only seen this as the factors of this quadratic expression. In the earlier videos, we just saw 3x plus 2 times 2x plus 1 as the factors of a quadratic expression. But using the lens of the grid method, one can also say that a quadratic expression can also be perceived as the area of a rectangle whose dimensions are its factors. I would like to know your thoughts about the grid method, about this interpretation of a quadratic expression in the comments below. I'm going to see you all in the next video.